Hello, ladies and gentlemen. Today our notes are going to be on something called the intermediate value theorem. It's a really straightforward theorem that makes a lot of just natural common sense. So this should be a good lesson. Let's get started. Okay, the intermediate value theorem. Please make sure that you get this written down and draw the diagram so you really have a good picture of what is going on. It says if function f is continuous. Huge concept. The function must be continuous, and you'll see why in a second. On a closed interval, a to b. So remember, this is an interval notation. It's saying that we are starting as an x value of a and ending at an x value of b. Then f takes on every value between f of a and f of b. Now, f of a is a y value, of course, dependent upon the x value a. So when the input is a, the output is f of a. And so what it's saying is it will take on every y value between f of a and f of b. So all of these y values will be included on the interval a to b. Okay? So, having said that, if f is continuous on a closed interval a to b and k is between f of a and f of b, so there's some value, some y height of k between f of a and b, then there is at least one c, okay, one x value in the open interval a to b. In other words, it can't be a and it can't be b. It has to be open, such that f of c is equal to k. So this is really straightforward, okay? What is this saying? Basically, the concept is, all right, if I have a graph here, just a real basic graph, and I start off by telling you that I know that f of 1 is equal to 3, okay? So at x equals 1, I am at a height of 3. Okay, and then I also tell you that I have a value f of 5 is equal to 7. Okay, so at f of 5, which we'll put right there, we're going to say we're at a height of 7. So 3, 4, 5, 6, 7. Okay, and I have that point. So those 2 points are on this graph. Okay, and I also tell you that f is continuous. Okay, so what the intermediate value theorem, the IVT, is telling us is that every y value between 3 and 7 will be used somewhere for some x value between 1 and 5. That makes sense. Let's just think about it, okay? I have this graph, and I have to connect these 2 points because it's a continuous function. These are just 2 of the points on the function f. So I have to go ahead and connect them. Obviously, I could just draw in a straight line, but I might also have like more of a curve. I might have a U shape, okay? There is somehow a connection between these 2. And so we don't know what exactly happens, but somehow I am going to get from here to here in a continuous function. So I'm just going to sketch in one possible situation. Okay, so that's one way. Now, what this theorem is saying, first of all, every y value, every height between f of 1 and f of 5, between 3 and 7, is in fact it's taking on every one of those values. The second part of this theorem is just saying that if f is continuous, okay, and k is a y value between f of a and f of b. So I'm going to say that k is right here, okay? Then what it's saying is then there has to be an x value, okay, which they are calling c, in the open interval a to b such that f of c is equal to k. And it had to be that c was between 1 and 5 and that k is between f of a and f of b, in this case 3 and 7. Okay, so you can kind of see how this makes sense. Like I said, it's a continuous function. You have to get from point A to point B. You have to get from height 3 in this case to height 7, or f of a to f of b. And so you're going to have to hit every y value in between. All right, so that's the concept here. Now we're going to do a couple application problems to see how it's asked. And what's really important with these is that you have a very scripted answer that we're going to use over and over again. It's going to get tedious, but if you use that answer, you'll always get your full points. Okay, number 1 here says, the table below shows several measurements of the velocity of bicycle riding on a straight road. V of t is continuous on the interval 0 to 20. Okay, so my x interval, okay, is from 0 to 20, and it's saying that it is continuous, that v of t, which is the velocity of the bike, is continuous between those x values. For 0 less than a t less than a 20, must there be a time t when v of t equals 2.5? Justify your answer. Okay, so this is just simply asking, between the x values, the t values, 0 and 20, must there be a velocity of 2.5? So what we're going to look here is basically, are we going to find a time when 2.5 would fall in between two of the other velocities? So you just kind of got to look to compare two velocities at a time. So if I compare these first two, would 2.5 fit in between those? No. If I compare the next two, does 2.5 fall in between 4.2 and 2.7? No. Okay? If I compare the next two, does 2.5 fall in between 2.7 and 2.3? Absolutely. There is one place where 2.5 is going to fall. Now, we don't just stop. We continue looking to see if there's any others. Okay? So, look at the next interval. Okay? Will 2.5 fall here? Yep, there is another spot where it's going to fall. And then lastly, between 3.8 and 4.6, no. So there is actually two t values, okay, when v of t will equal 2.5. And we know this because it's a continuous function, and the IVT tells us this. Okay, so here's how we're going to say. Okay, yes, there must be a time t when v of t is equal to 2.5. Okay, so yes, there must be a time. So we have to actually answer the question, and did you notice what I did? I just literally copied the question back. It's like an elementary school tactic, right? So I just copied back exactly what they said. Now this justify your answer. Here's where we're going to get into saying why we know it and where is the location. Okay, so we're going to say v of t is continuous. Again, restating what we know. And it's only because it's continuous that we can use IVT. So v of t is continuous, and by IVT, okay, now here's where you're going to state your intervals where 2.5 would fall in between. And watch how we're going to do it. We're going to say v of 7, which we know v of 7 is 2.7. Okay, so v of 7, 2.7 is bigger than 2.5, which is bigger than v of 9. And check, what is v of 9? v of 9 here is 2.3. So I think we agree, okay, that 2.7, which is v of 7, is larger than 2.5, which is larger than v of 9, which is 2.3. All you're doing is safely showing that your height, your k value, if you go back to the theorem, of 2.5 safely falls in between two existing y values. Okay? And we can state another one. So, and, okay, now we're going to start with v of 9. v of 9. This time 2.3 is less than 2.5, which is less than v of 14, which of course is 3.8. And that's it. Okay, we have answered the question. We've stated how we know, because it's continuous, the function is continuous, and there's the intermediate value theorem. And we've given an interval in which the 2.5, a velocity of 2.5 would safely fall between. Okay, let's move on to the next one. For 0 less than t less than 20, must there be a time t when v of t equals 5? So you can see very common language, and this is a very common way that the AP will ask this question. Okay, so for a time interval from 0 to 20, must there be a time when the velocity is going to be at 5? So again, we're going to compare our values. So we're going to look in between different time intervals. So between a time of 0 and 5, does a velocity of 5 fit between those two existing velocities? No, absolutely not. 5 is not between 3.3 and 4.2. Between a time of 5 and 7, does 5 naturally fit between 4.2 and 2.7? No. Between the next two? No. Between the next two? No. Between the next two? No. Not to say that it's not possible that a velocity of 5 was reached. Okay, it could have gone up to a velocity of 5 and then come back down. Here, between 3.3 and 4.2, it could have gone up to 5 and come back down, but it cannot be guaranteed. It cannot be guaranteed. So I'm going to answer this question saying exactly what I just said, okay? No, there is not a guaranteed time t in 0 less than t less than 20 when v of t is equal to 5. Okay, and then I just have to say, why do I know? And I would say, by the intermediate value theorem, IVT. Okay, and that's enough to say it. Okay, the answer is no. And you are sure of that because of the intermediate value theorem. All right, the next one is interesting and is asked quite a few times. What's the least number of times where v of t is exactly 4 meters per second? Justify your answer. So it's pretty similar to the first one that we just did, the letter, if I call this letter A up here. Okay, it's pretty similar to that first one. I'm doing the exact same thing. I am comparing, okay, again, between, and finding how many times 4 would fall in between. And so here I can see, if I use now a third different color, okay, between 3.3 and 4.2, does 4 fit? It absolutely does, so I'm going to put a star up here, okay. Between 4.2 and 2.7, yep, I would say it fits there, so I'll put a star there. Between 2.7 and 2.3, no. Between 2.3 and 3.8, no. Between 3.8 and 4.6, yes, a 4 would fit in between that. So, what is the least number of times? Now, again, is it possible that there are more? Yes, but this is the guaranteed least number of times, okay? So, there are at least 3 times in 0 less than t less than 20 where v of t is equal to 4. Okay, how do I justify that? I say v of t is continuous and by IVT. And now you're stating your intervals, okay? So I'm going to name all 3 intervals. So the first one was v of 0, and v of 0 is 3.3, which is smaller than 4, which is smaller than v of 5. Okay, let's name the next one. V of 5, which of course is 4.2, which is bigger than 4, which is bigger than v of 7. And last one is between 14 and 20 seconds. So v of 14, which is 3.8, which is smaller than 4, which is smaller than v of 20, which is 4.6 meters per second. Okay, so that then is our answer. We've again answered at least 3. We've given a reason because it's continuous by the IVT, and we've given our 3 intervals. Okay, let's move on to number 2. Okay, I'd actually ask you to go ahead and give this one a try. The number of people waiting in line at the try and save at the day after Thanksgiving is modeled by a continuous function L of t for 0 less than or equal to t less than or equal to 7. Values of L of t So L of t is supposed to be like the number of people in line. Okay, at various times t, different times, are shown in the table from 0 to 7. What is the fewest number of times at which L of t is going to equal 50? Give a reason for your answer. What I'd like you to do, this is exactly like the one we just finished. I want you to pause the video. I want you to do it, and I want you to write up your full response. And then I'm going to come back, and I'm going to give you the correct response, and I want you to compare it and see how close you were. So go ahead and pause your video, and then come back to me when you're ready. Okay, so let's take a look at my answer and see if you agree and have the same wording. Okay, so we're checking the wording as well as the answer. Okay, so I basically looked at my L of t, my number of people waiting in line, and I looked for an interval where 50 would fit in between. And I saw that between 37 and 84, 50 fit. And I saw again between 121 and 46, 50 fit. So I was able to say there are at least 2 times for the interval, so you always want to state the time interval, for which L of t equals 50. Again, just parroting back the question with my answer. L of t, why can I give a reason for my answer? L of t is continuous, must say that, and by IVT, and then your intervals of time. Your intervals where the number of people in line fluctuates below and above 50. So L of 1 is smaller than 50, because that's 37, which is smaller than L of 3, which is 84. 50 also falls between L of 5, because L of 5 was 121, and L of 7, which is 46. Okay, so hopefully your answer looked like that. We're going to move on to the next one. Okay, this next one is a little bit different, but I have seen ones like this on the AP exam. It says the function f and g are continuous for all real numbers. The function h is given by h of x equals g of f of x minus 3. So the composition of continuous functions, okay, or operations adding, subtracting, doing the composition of them maintains the continuity of the function, okay? So in this case, h of x is made up as the composition of g of x and f of x, and so it would still be continuous, all right? So very interesting, and this here is definitely something we're going to use. Now, the next question says, must there be a value r for 1 less than r less than 3 such that h of r is equal to negative 2? Explain your reasoning. Okay, so they are specifically targeting that h function, which I don't have a column for my h function. So I definitely need to look at my values. Now specifically, I'm only asked for the values between 1 and 3. Okay, so I only care specifically about h of 1 really. I want to know what is the height when r is 1, and I want to know what is the height when r is 3. And basically I want to ask myself, after I find those two values, does negative 2 fall in between those two heights? Okay, so h of 1 I'm going to go ahead and evaluate using this rule right here, that h of r, okay, h of 1 should be found by g of f, of 1 minus 3. Okay, so in this case, f of 1 is 2 minus 3. Okay, now g of 2, so go to your g of x. G of 2 is 9 minus 3 is going to be 6. Okay, now I have to evaluate h of 3. So same thing, it's going to be g of f of 3 minus 3. So again, we go through that. What's f of 3? F of 3 is going to be 4. So now g of 4 minus 3. G of 4 is going to be negative 1. Minus 3 would be negative 4. Okay, so I now have a height. H of 1 is 6, and h of 3 is negative 4. Okay, the concept here, the question is, okay, by the intermediate value theorem, can I guarantee that negative 2 will fall in between these? Well, is negative 2 a number that is smaller than 6 but bigger than negative 4? And I would definitely say, hopefully you all would too, yes, that is true. Okay, negative 2 does fall in between there. So if that's the case, that I can say yes, I'm going to say, yes, there must be a value r for 1 less than r less than 3, such that h of r is equal to negative 2. Okay, now I'm going to get into my reason. Because h is a continuous function and by IVT, so I always have to state the theorem, and now I'm going to go ahead and give my interval. So I'm going to say h of 1, which is 6, of course, was bigger than negative 2, which is greater than h of 3, which is, of course, negative 4. So there it is. That's the complete answer and reasoning and interval. Okay, next question says, must there be a value r for 2 less than r less than 4 such that h of r is equal to 1? Explain your reasoning. Exact same type of question as the first one we just did. Okay, I want you to pause the video and do the exact same thing. You're going to have to evaluate h of 2 and h of 4, and then you're going to have to decide if one falls in between those two answers, and then write up a response. Okay, so pause your video, get to work on that, and come back. Okay, so let's go ahead and compare our work for yours and mine. Okay, so if you look here, it says that must there be a value, okay, for r between 2 and 4. So those are the x values that I had to plug into my given function for h. So I evaluated g of f of 2 minus 3. I got 10 minus 3, which is 7. And then g of f of 4 minus 3. G of f of 4 was 6, minus 3 is 3. So I looked at those outputs, those y values, those heights, if you will, 3 and 7, and I said, is 1 going to fit in between there? And I definitely can conclude that no, it does not have to fit in between there. So I can conclude then that no, there does not have to be a value r for the interval 2 to 4, such that h of r equals 1 by IVT. If your justification is by IVT and there wasn't an interval, you can stop there. Notice that if the answer was yes, then you end by stating the interval. If the answer is no, then by IVT is your end of the sentence, end of your justification, and you're done with the problem. Okay, we have one last quick one to do, and we are all done. Okay, this last question says, the function f is continuous. Again, there's that magic word. The function is continuous on the closed interval, negative 1 to 2. Some values of f are shown in the table. Okay, so you can see they give us this values here. All right, the equation f of x equals 5 halves must have at least 2 solutions in the interval 0 to 2. Okay, so now they're actually changing the interval from the whole table, only from 0 to 2. If k, notice that we have a unknown here, number here, if k equals what? So what would k have to be in order for there to be at least 2 solutions? In other words, at least 2 times when f of x, when the height was equal to 5 halves. I want you to pause the video, try and come up with this answer on your own, and then see if we agree. Okay, so you can see here that I selected the answer of 2. Why does that make sense? Well, if this k value here was a 2, then 5 halves, which is of course 2.5, would fall in between these two heights and also in between these two. And so we would need that to be smaller than the given y value in order to fall in between those. Okay? And so hopefully you were able to come up with that solution. Okay, ladies and gentlemen, that concludes this video for the evening. I hope that you understand the intermediate value theorem and are able to apply it. And if you have any questions, please make sure you save them and ask them for me next time you see me. Hope you have a fantastic evening, and I will see you next time.